Greetings and salutations, magical chemists. Today we get to talk about entropy. Entropy can be considered the extent of randomness or disorder in a chemical or physical system. The second law of thermodynamics states that the entropy of the universe will increase over time. So no, you're not just imagining things. Entropy is represented by the letter S, so delta S is a change in entropy. A positive delta S implies that there's increasing entropy, more chaos. A negative delta S implies decreasing entropy. And as the second law of thermodynamics states, nature tends towards increasing entropy. In chemistry, we talk about positional entropy. So the more positions available, the more space or the more places something can move, the greater the entropy will be. There's an equation that allows you to calculate the entropy change for a system, and it should look pretty familiar. It's very similar to how we calculate delta H. Delta S is calculated by taking the entropy of the products and subtracting the entropy of the reactants. And this equation is given on the formula chart. The units of entropy are a little bit odd. It is going to be given in joules per mole Kelvin. So this can also be written with the moles to the -1 and the K to the -1, but that just, of course, just means dividing. So you'll see it written both ways, but those are the units for entropy. The craziest thing is that the entropy of an element is actually not zero, unlike with delta H. This is where the third law of thermodynamics comes in. It says that the entropy of a perfect, pure crystal at 0 Kelvin has a value of 0. So at absolute 0, a perfect crystal has no entropy. Hopefully you're realizing that that means in the real world, everything has entropy, because we're never at absolute 0, and, well, nothing's perfect. So everything we work with, even elements in their most stable form, will have a positive entropy. Now, most of the time, you're not looking at an absolute entropy. I'm not even sure what that would mean. Instead, we're looking at the change in entropy. Is a system getting more organized or more disordered? So there are two most important things that you have to consider when you're trying to determine if entropy has gone up or gone down. Changes in state and changes in the number of particles. Remember positional entropy? The idea that if you can take up more space or have more possible positions, you have more entropy? Well, hopefully you can see that that means a gas has way more entropy than any other state of matter. Because the gas particles can be in a lot more places, and they're all over the place, they have tons of energy, all sorts of things. So being a gas, turning something from a not gas into a gas, is the number one way to increase entropy. But aqueous things, so dissolving something, that's going to have more entropy than something that's just a pure liquid. And of course, any state of matter will have more entropy than a solid. As far as number of particles, well, again, positional entropy. If you have more particles, you have more places for particles to be, more possible positions for them to be found in relative to each other. That means increase in entropy. Let's look at this visually. So anytime you're increasing, honestly, the amount of energy in your system, so you're going from a solid to a liquid to aqueous to gas, you are increasing the disorder, the randomness, the chaos. All of those are positive delta S. And of course, if you go the other direction, if you go to a lower energy state of matter, you're decreasing entropy. Visually, it can help to see something that's dissolving. Well, if it was a solid, it's very organized in that liquid. And then as it dissolves, it has more possible positions, more chaos, more entropy. Similarly, if you start with a system that has 3 particles, and that diatomic whatever breaks apart into single atoms, now you have 6 particles. More particles, more possible positions for things to be in, increasing entropy. So if you wanted to put it all together, it would look like this. Solids are the lowest, then liquids, then aqueous things, and then gases have tons of entropy, and more moles of gases have even more entropy. I want to make a note when we were looking at those 2 biggest factors for evaluating change in entropy This is primarily when you're evaluating a change in chemical reactions, from reactants to products. However, you won't always be comparing, like looking at a chemical reaction to see the change over time. Sometimes they'll just give you two different things, like here are these two different compounds, here are these two different systems, which one has more entropy? So there are some other factors that you can use to compare entropy in those cases. So if you're comparing individual molecules or materials, something at a higher temperature will have more entropy, because at a higher temperature there's more motion, more possible arrangements. And, as we talked about, energy will increase as something dissolves, more possible arrangements. Now, when you're considering the entropy of a gas, we have to consider changes in both pressure and volume. So, interestingly enough, entropy will go down if you increase pressure, because entropy goes up if you increase volume. Wait, what? Remember, whenever you're changing pressure, think about what that would do to volume. If you decrease the pressure, now it's taking up more space. More space, more possible positions, thus more entropy. Interestingly enough, entropy is actually higher when you have weakly bonded compounds compared to strong covalent bonds. If the bonds are weak, the atoms basically have more wiggle room, more possible positions, more entropy. And entropy increases as the complexity of a molecule increases. And there's a lot of different factors here. You could look at the number of atoms in a molecule, the number, like how heavy are the atoms in a molecule, how many electrons are in the molecule, all the things. Let's take a look at some examples. If you are comparing diamond and graphite, well, diamond has covalent bonds in 3 dimensions. The atoms are very much fixed in place. Graphite only has 2-dimensional sheets. So graphite has more entropy because there are fewer bonds, thus more possible arrangements. Butane gas at 1 atmosphere, lower pressure, is going to have more entropy than butane gas at 2 atmospheres. Because if you've lowered the pressure, well, now you've increased the volume, more possible positions. Finally, comparing 2 diatomic halogens, fluorine gas and chlorine gas. Well, chlorine is bigger, right? Another extra energy level full of electrons. It also has more mass. So more electrons, more molar mass, more possible arrangement of all those different particles. Thus, more entropy. Okay, hopefully this idea of determining which things have more versus less entropy, that change in entropy, is starting to make a little sense. So we're going to try some practice problems. First, you're going to start off, you're going to look at each of these chemical reactions. Now remember, for chemical reactions, you're looking primarily at the change in 2 things, changes in state and changes in number of particles. So I would like you to go ahead and determine, do you think entropy is going up or going down for all 3 of these, and, oh yeah, why? Whenever you are ready to check your answers, unpause the video. Did you see that the first reaction is decreasing in entropy? It's a gas to a gas, but you had 2 particles of gas going to 1 particle of gas. Decreasing number of particles, decreasing entropy. Okay, the next one was kind of a trick. You're going from 2 particles of gas to 2 particles of gas. So the entropy is actually about the same. Now the last one looks kind of complicated, but hopefully you could tell that entropy is definitely increasing. In the reactants, you didn't have a gas, but in the products you did. And that is enough to justify entropy as increasing. Okay, for the second practice problem, now we're not looking at chemical reactions. We're just comparing individual things or individual systems. So that's when you need all those other rules at the top of the page. So go ahead and try it. You're going to put, for A, B, and C, you're going to put the things provided in order of increasing entropy. So whenever you are ready to check your answer, go ahead and unpause the video. Well, you should pause the video first. Forgot that part. For the first one, lowest to highest entropy would be CH4, then C2H6, then C3H8, because as you increase the number of atoms, you're increasing the entropy. For the second one, we're looking at 4 ionic solids. And the only difference is that they're changing what alkali metal the chloride ion is hooked up with. So the idea is, as the alkali metal gets bigger and bigger and bigger, we're having greater and greater entropy, because as you have a greater molar mass or a greater number of electrons, you're increasing entropy. For the last one, the highest pressure is the lowest entropy. So it goes from 3 atmospheres to 1 atmosphere to 0.25 atmospheres, because decreasing the pressure increases the volume, thus more possible positions and more entropy. Now you might be wondering why we are so fixated on determining change in entropy, but it turns out that has a lot to do with the spontaneity of a reaction. So go ahead and check out the next video on Gibbs free energy to learn more. Thank you for playing with the glories of chemistry.